始めたいと思います。セッション3の講演者はアレックス・ローゼンさん、セバスチャン・プフルクバイルさん、津田俊秀さん、キース・ベイバーストックさんです。そして、モデレーターは上田明文さんです。では上田さん、よろしくお願いします。
皆さんお疲れでしょうけれども、最後のセッションどうぞよろしくお願いいたします。モデレーターを担当します上田と言います。市民科学研究室の代表をしております。で、今日のセッションの1では、現在のですね、事故をめぐって起こっている、それを過小評価する向きとか、それから矮小化しようとする向き、それに対してですね、どう言説や情報の、流通が関わっているかという話が、主に社会学的な観点からお話がされたと思います。そしてセッションの2では、被爆している人、そして避難している人の人権が
And there are people evacuated from the affected areas and the human rights for those people are neglected. We discussed first of all the fact that their human rights are neglected, and we further discussed the laws about that. And then in the last session, underlining disease that is a public health by the radiation, and scientifically what those radiation impact is proven or not, and if there are any uncertainties, what kind of a health care or intervention should be provided in terms of the good public health. We are talking about these issues in session 3. We are honored to have this distinguished guests including the expert coming from overseas, and I believe we can have an in-depth discussion. I said there are 4 presenters, and actually physically there are only 3 speakers, and 1 person will join us through the Skype. Dr. Alex Rosen, you will see the video clip by this doctor, and after that, in the open discussion, Dr. Alex Rosen will join us through Skype. Dr. Rosen, can you hear us? You are connected with us? Are you sure? Are you with us? Can you hear us? Dr. Rosen? Hello? Now I'd like to start with the video clip by Dr. Alex Rosen, if it's ready. Yes, thank you very much.
アレック・ローゼンと言います。ドイツの小児科医をしています。そして核戦争防止国際医師会議のドイツ支部のそしてアンスケアレポートに関する批判的な追及を行いました。アンスケアは原子放射線の影響に関する国連の科学委員会です。そして2014年の4月に福島の事故に関するレポートを出しました。そしてこの中の結論として健康被害は福島の放射線の放射によって起きるものではないという結論を出しています。我々は医師として患者の健康
Going through the report, we have identified 10 critical issues that I will now in detail discuss with you. The first issue that we found critical is the validity of the so-called source term. Now, the source term represents the amount of radioactive material actually released during the nuclear catastrophe. On the left-hand side, you can see a photo of the plume carrying radioactive isotopes from the nuclear plant into the atmosphere. Isotopes like iodine-131 or cesium-137. And on the right-hand side, you can see the trajectory of some of the radioactive fallout over mainland Japan. Now we know that the Japanese population was relatively lucky because almost 80% of radioactive fallout actually occurred over the Pacific Ocean rather than over landmass. However, there was still substantial amounts of radioactive material deposited over Honshu Island. And in order to calculate or estimate the expected health effects, you first need to know how much radioactive material actually was released. Now, several institutions have dealt with this question. One being the Independent Research Institute in Norway, NILU, an institute dealing with air research and geology, and another being TEPCO and the Japanese Atomic Energy Agency, an organization that is very close to the Japanese nuclear industry and which has actually been criticized by the Japanese parliament for collusion and corruption after the Fukushima Daiichi nuclear catastrophe. Now, what UNSCARE did in its report is it based its entire body of conclusions not on the findings of the independent research institutes in Austria or Norway, but solely on the numbers published by the Japanese Atomic Energy Agency. And you can see here in this graph that while NILU, the independent Norwegian institute, estimated the amount of radioactive cesium-137 to be 37 petabecquerel, JAEA published numbers that are more than 4 times lower. And the same is true for radioactive iodine, where again JAEA published numbers that are by factors lower than the numbers even published by TEPCO. And this, in our view, represents a systematic underestimation not only of the source term, but obviously also of the expected health effects. The second issue is that of the ingestion of radioactive material through food and water. Similar to the estimation of the source term, in order to adequately calculate the expected health effects, you first need to know how much radioactivity was actually taken up by people through food and water. And in order to do that, you need a good database that shows you how much radioactivity certain types of food actually contained at certain points of time. Now, what UNSCARE does is it bases its entire conclusions on one single source of information. And this is the food database compiled by the International Atomic Energy Agency, the IAEA. And again, the IAEA cannot be considered a neutral source of information because in its founding document, the IAEA states that its purpose is to promote nuclear energy all over the world. On this graph, for example, you can see that the data published in the IAEA and WHO report coming from the IAEA food database is substantially lower than the estimates, for example, by the Japanese Ministry for Science and Technology, MEXT. Almost 5 times lower. These are maximum radioactivity readings in leafy vegetables in Fukushima prefecture. The third issue is that of the health effects of the workers on site at the Fukushima Daiichi nuclear power plant. You can see in these pictures the working conditions of the more than 24,000 people coming into contact with radioactivity on a daily basis. Now, more than 70% of these workers are actually not directly employed by TEPCO and do not fall under TEPCO's relatively strict radiation regulations, but are employed by subcontractors or subcontractors. And in many cases, we have heard reports about dosimeters covered up by lead in order to falsely measure lower amounts of radioactive exposure. We have heard reports about subcontractors not issuing health reports, not letting their workers go to regular health checks. So the fact that UNSCARE bases its entire body of conclusions regarding the health effects of workers on the data supplied by TEPCO itself is of great concern to us as scientists and doctors, many of us occupational physicians, who know that in order to adequately assess the health of the workers, you cannot rely on the company that actually put these workers in danger because of its short-sighted policies. And the company we're talking about, TEPCO, has actually been criticized severely by the Japanese Parliament's Investigation Commission for being mainly responsible in causing this nuclear catastrophe. The fourth issue is the effects of radioactivity on the non-human biota, meaning animals and plants. Now this is important not only from an environmentalist point of view, to look at the severe damage that the nuclear catastrophe has caused on the environment, but also from the scientific physician's point of view. Because if we better understand the effects of radioactivity on living beings, on animals, on mammals especially, we come to a better understanding of the effects of radioactivity on humans. Now, UNSCARE basically negates any effects of radioactivity on the non-human biota by stating that everything has been said in their reports from 1998 and 2008, acting as if no new scientific evidence has come out since then. Just very recently, 2 studies have come out dealing with the amount of, or the animal population size in Fukushima, comparing it to the animal population size in Chernobyl, and you can see that similar effects are seen in butterflies or birds, namely that there is a decrease in population size in the affected regions, most probably coming from increased amounts of radioactivity. And the second study I briefly want to touch upon is one performed on monkeys in near Fukushima City that show increased levels of cesium-137 in their muscle biopsies. They were compared to a group of monkeys living in the north of Japan under similar conditions, which had lower levels of cesium, or no measurable levels of cesium in their muscles because they were not affected by radioactive fallout. And you can see that the monkeys living in the forests around Fukushima City have discernibly lower levels of blood cells, mainly red and white blood cells, than the comparison group in northern Japan. And these studies are very important to us as physicians because they help us understand the effects of radioactivity on human beings, or on living beings, especially on mammals, and we can draw conclusions for human health from these studies. So we're greatly concerned that UNSCARE completely leaves out all of these studies and all of these findings in its report. The 5th critical issue in the UNSCARE report is the vulnerability of the unborn child, especially the embryo. Now, we know for many decades already that the unborn child has an increased sensitivity or vulnerability to ionizing radiation. Even in the 1950s, Alice Stewart found that a single X-ray to a pregnant woman's womb would double the risk for childhood leukemia in her child. Now, UNSCARE goes to great lengths in its Annex B to discuss the increased level of sensitivity of children as opposed to adults to radioactivity, showing that children who are exposed to the same level of radioactivity display higher percentage of leukemia, thyroid cancer, brain cancer, breast cancer, and neurologic or psychological effects. What UNSCARE completely ignores and negates is the fact that the unborn child has an even higher sensitivity to ionizing radiation. This is due to the high metabolism, the high turnover of cells in the embryo, which is developing, and this of course leads to a higher risk for mutations in the genome, in the chromosomes. The immune system and the cell repair mechanisms are not yet fully developed in the unborn child, so they cannot adequately protect the child from cancer that is developing. On the picture on the left-hand side, you can see the simple graphic that illustrates how radioactive particles can travel through the woman's blood supply into the womb and hence into the child. For example, iodine-131 ingested or inhaled by the mother actually accumulates in the fetal thyroid gland and can lead to the development of thyroid disease or thyroid cancer after birth. And cesium-137 freely passes through the blood supply into the placenta, into the embryo, accumulates in the amniotic fluid, in the bladder, and affects the unborn from all sides with beta and gamma radiation. in dismissing all of these physiological differences between the unborn child and the infant, the authors of the UNSCARE report effectively underestimate the health risks of this particularly vulnerable population. In fact, studies on the hibakusha of Hiroshima and Nagasaki actually show that the non-cancer health effects, namely through cardiovascular disease, stroke, and heart attacks, are just as high as the health effects through cancer diseases. We know that ionizing radiation, even at very low levels, causes measurable damage to the cell's genome, to the chromosomes, to the DNA. And you can see on the right-hand side a graphic of how radioactive isotopes damage the DNA. And we know that damage to the DNA can lead to mutations and to cancer, but also has numerous other effects on the metabolic system, on the cardiovascular system, can have effects, if we're talking about the reproductive cells, on virility, on perinatal mortality. There are numerous studies that show cognitive effects, increased rates of spontaneous abortion, of miscarriages, of perinatal mortality, of cardiovascular disease in people who are exposed to increased levels of low-level ionizing radiation. Still, UNSCARE states in its report that it expects to see none of these. And because they did not expect to see any of them, they did not look into them. The second contentious issue in the UNSCARE report is the misleading comparison to background radiation. UNSCARE states in several parts of its report that the expected amount of ionizing radiation that the population is confronted with compares to or is below levels of naturally occurring background radiation. Now, this leads the reader to conclude that it is not dangerous, because if it's lower than natural background radiation, it cannot be harmful. But this is a misunderstanding, because in fact we know that there is a linear relationship between the level of ionizing radiation that an organ or a tissue is exposed to and the risk of developing cancer and other diseases. And this relation, this dose-response relation, goes down to even the very lowest levels of ionizing radiation. There is no threshold below which we can say that radiation is harmless. That also means that background radiation, represented here in this picture by cosmic radiation, terrestrial radiation, natural radiation in food, natural radiation from radon gas coming out of the ground, are all known causes of increased levels of cancer. And on the right-hand side, you can see a study from the United Kingdom that shows different levels of natural background radiation leading to increased levels of childhood leukemia. This study came to the conclusion that a number of cases of childhood leukemia are actually caused by natural background radiation. And this is the case for all types of cancer. The level of natural background radiation in Japan is approximately 1.5 millisieverts per year. Now this is about the same as 75 chest x-rays. And you would hardly find a doctor that would do 75 chest x-rays on a child by stating that this would only represent the amount of natural radiation that a child is exposed to within a year anyways, so no harm is to be expected. This is simply not how ionizing radiation works. You need to decrease the dose of every individual as low as possible. Against natural background radiation, we can do relatively little, but we must prevent additional sources of ionizing radiation. Our eighth point of criticism is UNSCARE's interpretation of the findings that it presents in the report. In its press release, UNSCARE comes to the conclusion that, quote, no discernible changes in future cancer rates and hereditary diseases are expected due to exposure to radiation as a result of the Fukushima nuclear accident. and that no increases in the rates of birth defects are expected. It is important to realize that this statement is not saying that there will be no health effects, but only that these health effects will most likely not be detected by commonly used epidemiological methods. And this is an old trick that we've known for many decades from the tobacco industry, the automotive industry, the asbestos industry, who all argue against a causal link between their product, cigarette smoke or asbestos or exhaust fumes, and lung disease. No cancer carries a label of origin. It is impossible to determine the exact cause of one single cancer. But if you look at epidemiological research on a certain population, you will be able to find evidence that an increase in unhealthy living standards, for example, the amount of cigarette smoke or the amount of ionizing radiation that you're exposed to, shows an increased level of cancer risk. Another important fact is that when you compare the 292-page full report to the 22-page summary or the 1-page press release, miraculously, the level of certainty that is represented in these documents seems to increase the smaller the document gets. In its report, UNSCARE actually admits that there was incomplete knowledge about the release rates of radionuclides over time and the weather conditions during the releases, and that there were insufficient measurements of gamma dose rates and of radionuclides in the air during the passage of the radioactive plumes for an assessment to be made of the external exposure based on environmental measurements. Also, the author states that relatively few measurements of foodstuff were made in the first months, and that there was insufficient information on the transfer of radionuclides to food. All of these uncertainties, however, are in no way represented in the summary or the press release. The next critical issue is the misrepresentation of the actual protective measures taken by the authorities. In its report and its press releases, UNSCARE applauds the protective measures taken by the authorities. The Japanese Parliament's Investigation Commission, however, finds that the central government was slow in informing the municipal governments about the nuclear power plant accident and failed to convey the severity of the accident. The Commission concludes that the situation in Fukushima deteriorated because the crisis management system of the Kantai, the regulators, and other responsible agencies did not function correctly. The damning criticism of the Parliament's Investigation Commission goes on to state that the government and the regulators were not fully committed to protecting public health and safety and have not acted to protect the health of the residents and to restore their welfare. One example is the lack of distribution of stable iodine tablets after the nuclear meltdown. According to UNSCARE, medical countermeasures included the use of stable iodine for thyroid blocking. But only careful readers of the report will notice that this stable iodine was only given to 2,000 emergency workers, not to the general public. In fact, the Japanese Parliament's Investigation Commission concluded that although the positive effects of stable iodine were fully known, the government's Nuclear Emergency Response Headquarters and the prefectural government failed to give proper instructions to the public. And this error caused thousands of children to become irradiated with iodine-131. Unlike the members of UNSCARE, we are disturbed by the evidence that the authorities have not made public health and safety their top priority. Instead of adequately protecting the people affected by the radioactive fallout, the annual exposure limits were raised to 20 millisieverts on April 19th in 2011, effectively forcing many children to live in radioactively contaminated areas. Our 10th and final point of criticism of the UNSCARE report is the lack of meaningful conclusions for the affected population. UNSCARE does go as far as to cite the expected or estimated amount of radiation for the entire Japanese population due to the nuclear catastrophe. but falls short of translating these numbers in sievert and gray into something that people actually can understand. On the left-hand side of this graph, you can see the radiation estimates of the UNSCARE report, the total collected dose, and you can see in the middle column the risk factors derived from the internationally acknowledged Bayer 7 report. And with these two factors, you can actually calculate the number of cancer cases that you expect in a given population over a given time. And using the numbers of the UNSCARE report, which again we expect to be systematic underestimates of the true extent of the health effects, we still come to a number of between 4,000 and 16,000 additional cases of cancer. UNSCARE calls these no discernible increase in cancer rate, but we see 4,000 to 16,000 families bereaved by cancer that they would not have acquired without the nuclear catastrophe. And in the line below that, you can see the mortality rate. And using the mortality risk factor from the Bayer 7 report, you come to a number of between 2,500 to 9,000 people who actually die as a cause of their cancer. UNSCARE also calculated the collective thyroid dose of the entire Japanese population, and you can see in the bottom part of the table that using the UNSCARE numbers, we come to about 1,000 additional cases of thyroid cancer in the Japanese population in the coming decades. And again, this number is by no means trivial if you consider that each one of these will have to have their thyroid removed surgically, will have to take medication for the rest of their lives, will have relapses, and 7% will actually die from thyroid cancer. I hope that by going through these 10 critical issues, you were able to see where the fault lines of this UNSCARE report lie and why we have so severely criticized this report. We do not see it as a valid basis for drafting policy, for advising policymakers on how to react to nuclear catastrophes in the future or how to prevent them. We do not see that the UNSCARE report in any way helps the people living in the affected regions. These people do not need a report whitewashing the crimes of the nuclear industry. What the people of Fukushima rather need is proper information, health monitoring, support, and most of all, what they need is the acknowledgement of their right to a standard of living, which is adequate for their health and their well-being. And this is a universal human right. And what we see is that a lot of people in the regions affected by nuclear fallout are currently denied this very right. But this right to a standard of living adequate for their health and their well-being should be the guiding principle in evaluating the health effects of the nuclear catastrophe, not the industrial interests and not political gains. I thank you for your attention, and I look forward to your questions and comments later on in our video conversation. Arigatou gozaimasu.
ローゼンさん、どうもありがとうございました。今お聞きになりましたように、今年公表されました国連科学委員会UNSCAREの報告書に対してですね、いろんな角度からの全面的な批判ということでお聞きいただいたと思います。で、染料とその健康影響の出方については、対応関係については、このセッションの一番最後で、さんがより詳細に、
and health effects. We will have our final session given by Keith Baverstock, and we will learn even more in detail about that. Similar to the earlier session, we will ask for all of the questions to be sent in, and then we will do a final Q&A at the very end. So we will now turn it over to Dr. Sebastian Flugbeil. As you are aware, Germany has taken action to rid itself of nuclear power plants. He has been very active in this field. He will speak today not just about the accidents of the nuclear power plants and how that can cause radiation harmful effects, but there are actually many issues, even when it is in regular operation. For example, when there is an interim storage facility built, then there are many things that are occurring around that site. So he will be sharing with us the latest data from his research so that we can learn what could apply to our work in Fukushima.
Father has pressed me to speak English. If you understand not so much, he is responding.
It is difficult for scientists who disagree with orthodox views of the link between ionizing radiation or radioactivity and impaired health to carry out independent studies. One significant problem is the fact that there are no accurate registers for most diseases and that it is virtually impossible to produce such data on self without state funding. As a result, there are a large number of dubious mainstream publications, but far fewer publications in which radiation issues are presented more realistically. Studies carried out by a small group of German scientists led by the mathematician Hagen Scherp, who works in the Helmholtz Research Center in Munich, are particularly interesting against this background. He has been unable to attend this conference for personal reasons. We have therefore agreed that I shall present a report on his work. Scherp first developed an interest in radiation issues a few years after the Chernobyl disaster. Interestingly, the conservative state government in Bavaria commissioned the creation of a precise map of Chernobyl fallout in Bavaria. In addition to a registry to congenital deformities in Bavaria from 1984 to 1981. Scherp was able to access to this data. The research results were shocking. He was able to demonstrate that the number of congenital deformities has changed significantly as a function of the level of fallout from Chernobyl. These findings contradicted claims by Western European governments and science institutes who have consistently asserted that radioactive contamination in Western Europe following the Chernobyl disaster was so low that nobody would suffer any ill effects from it. The most alarming thing about Scherp's analysis was that the changes were observed in conjunction with exposure to just 1 millisievert, not 100 millisievert, not 20 millisievert, but 1 millisievert of radiation, well within an exposure range that seems to be perfectly safe. I give some examples. Congenital malformation. There is used the terminus birth defects proportion. That means number of birth defects divided through number of total births. That are the trends of male and female congenital malformations in Bavaria at all nearly 30,000 cases in 5 quintiles. That means 5 regions in Bavaria. The difference of these regions is a fallout dose after Chernobyl in these regions. You can the red number that are the that is not possible. The red numbers are the mean dose per year in the first years after Chernobyl. And you see from the left, 1, 2, 3, 4, 5, that the jump you can see in these graphs is increasing. And the last, yes. And the increase in the congenital malformation rates is proportional to the mean dose in these 5 exposure quantile classes from at all 96 Bavarian districts, and the number of the handicapped children are nearly 30,000, I have told about. And an important detail is you can calculate from this data, from the measured dose data in Bavaria and the number of congenital malformation, the risk for boys, the increased risk for boys was born with congenital malformation rates in a surrounding with 1 millisievert per year is increased with 32%. And the same for girls for 82%. If you live in a region with 1 millisievert per year, you have to calculate that your girl have an increased risk to have congenital malformation of 82%. That is very high, and I have made this the sign because it gives the first information that for girls is a question of radiation much more important as for boys. That is an example for a concrete medical problem that are heart malformations. I have written on the side 2 pollution data. The black points on the line below are the data from the 10 lowest polluted regions in Bavaria, and the black triangle are the data of the 10 most polluted regions in Bavaria in respect of heart malformation. You see that the pollution in these both groups of districts are not so far from each other. 4.5 kilobecquerel per square meter for the lower regions and 37 kilobecquerel per square meter for the higher polluted regions. But the difference is remarkable. And not only to tell about the girls that are congenital malformations in reproductive organs of boys, you see a jump in October 86, nearly the double of the values before. It is highly significant, this difference. The publication of these findings did not result in the introduction of a nationwide register for congenital defects in Germany. On the contrary, the Bavarian government stopped the registering congenital defects. Over the following years, SHERP analyzed the data of stillbirth data, infant mortality, the gender of newborns in multiple papers. The data are available in the official health statistic published by almost every state government. SHERP developed a method of identifying trend changes within the data. He is particularly interested in step changes with long-lasting effects. These findings have been presented in a large number of papers published in international peer-reviewed journals and conference proceedings. However, international specialist committees are having trouble coming to terms with the findings, typically ignore them, because they contradict the current orthodoxy on radiation safety. Nevertheless, his findings are difficult to deny from a number of different reasons. They are based on data published by the state. His analysis can be checked and replicated by anyone. He has discovered similar effects in almost every region in which populations are exposed to radiation. His studies can use data from exceptionally large population groups. And at last, the observed effects are being shown to be present in an increasing number of countries. I give some examples. Stillbirths, there's such a definition, stillbirths proportion you find on the graphs I show. That means the number of stillbirths divided through the number of total births. That are data from Bavaria once more. That are the least contaminated districts in Bavaria, and you cannot find any significant change point in the data. The mean fallout density is 4 kilobecquerel per square meter. And that are the 10 highest contaminated regions in Bavaria, and here can you see a significant change point in 1987. What means that? That means in these districts in Bavaria, additional about 100 cases of stillbirth. Oh, I have a mistake. So that is the same question, only for Denmark, Bavaria, GDR, East Germany, West Berlin, Hungary, Iceland, Latvia, Norway, Poland, and Sweden. That means a bigger part of Europe. You see a decreasing line of points. It is an index for the quality of the health service system in these countries. But 86, you see a step in the data. And what means the step that are excess stillbirths about in the region of 3,000 in these years in the countries I have told you. That is the same procedure once more in the Finnish population. There was enough data or exact data about the fallout from Chernobyl in Finland. It was possible to divide the population in 5 different groups. The red numbers are the fallout data from the month May 1986, and you see with the increasing data of the fallout dose, the steps of stillbirths are increasing too, and the last 2 steps are statistically significant. That is a good argument, this increasing line of dose and the increasing high of the step for the connection of radiation and this phenomenon. The youngest of the phenomena Sharp has looked for is a relation of newborn boys to newborn girls. Normally, a little bit more boys was born, about in a relation of 105 to 105 boys, 100 girls. I think I have shown you this graph before. In the line of the United States, you see that it's a light decline line. without any break. Here is 1986 is Chernobyl, and in the upper line you have the data of the biggest of 38 European countries. You see there's a change of trend exactly after the date of Chernobyl, the so-called Chernobyl gender gap. And if you think what that means that in the European countries about 270,000 girls was lost in the time of the embryonic development. If you would add the region of Chernobyl and the southeast republics of the earlier Soviet Union, then you come in a region of about 1 million children which was going lost. That is this problem picture for Russia. You see in the time before Chernobyl nearly a line, and then it goes up, and you can see not only the result of the big accident in Chernobyl in '86, but there was a little, a not so big accident in the same nuclear power plant. Nobody was informed about that. With the INES step 5, Chernobyl and Fukushima were INES step 7. You see that is a very, very carefully picture of the radiation situation. This is an example from Cuba. You will ask why Cuba. Cuba is far from Chernobyl, but the Russian has given over decades a lot of food to Cuba. And the Cuba food import from the Soviet Union, Russia, was in 1987 doubled as high as in the years before and after, and the price was a half of before and after. You can think over the consequences. That are the data from the prefecture of Fukushima. You see at the end the data go up, but the time is too short to make a plausible picture. Then as Sharp asked if there are so much effects after Chernobyl, then we should find any effects in the connection with the atomic bomb test, with the atmospheric atomic bomb test. And you see the result for Europe and for the United States, the same changing in the trend after the main time of the atmospheric atom bomb test. That is an example from German nuclear power plants. We have no final storage for high radioactive waste, and therefore each nuclear power plant in Germany has to build any big hall for interim disposal of the high radioactive waste. And the nuclear power plant Philipsburg has such hall too, and exactly in the middle of 2001, in the July of 2001, changed the line of the relation of newborn boys to newborn girls, with a radius of up to 40 kilometers, is it to see. That is the same for France nuclear waste disposal, and that are the last pictures. That are the picture for 32 nuclear facilities, not only nuclear power plants, but nuclear research center too, and storage of nuclear waste. You can see very clear a change in the relation in after up to a radius around the facilities up to 35 kilometers. That is another kind of of mathematics for that, and that was for Germany and Swedes. I think I have told nonsense. So for Germany and Switzerland are this curve, and that is the same procedure for 28 nuclear facilities in France. You have the same picture up to 35 kilometers around the facilities. You can show this changed relation for newborn boys to newborn girls. You can ask what is the reason for this effect in so many different countries with so much different medical question, in so much different in the vicinity of so much different nuclear facilities. It is radiation and that are all processes with influence of the genetic. And I have tried to make connection files, but I have broken my work because I had to. It would be black from so much files in this picture. Citizens ought to be able to decide whether or not they find the proven negative health effect acceptable. Yet every government is avoiding the corresponding public debates. Is it really so bad if the rate of stillbirths increases, or if about 1 million fetuses, the majority of them girls, fail to survive long enough to be born? This line of reasoning seems absurd, but the discourse takes place in the ethical, moral, and political arenas, all of which live beyond the science. Regardless of what socio-political decisions may be taken, Sharp's findings constitute a kind of thermometer that reveals regions in which normal patterns of human health have been thrown into disarray by radiation. The precise way in which this disturbance functions is not yet fully understood. However, there are reasons to suspect that the genetic code is scrambled in some way, and that the resulting changes not only include those examples demonstrated by Sharp, but also a whole raft of other diseases for which we simply do not have comparable, reliable data at present. The ramifications for established views on radiation safety are so radical that even many anti-nuclear groups are worried about citing Sharp's findings in support of their own arguments. It is difficult to grasp why the establishment puts up such robust resistance when it comes to radiation-induced genetic abnormalities. From a historical perspective, observations about the impact on the genome were among the earliest discoveries on the damaging effects of ionizing radiation on health. To this extent, Sharp is reminiscent of Hermann Josef Mahler, who was awarded a Nobel Prize for his work on mutagenesis, which already touched upon several of the effects for which Sharp is currently providing evidence. My hope is that a research like that of Hagen Sharp will contribute to an understanding of radiation damage in all its ugliness, and that the relevant authorities will draw the right conclusions from the avoidance of such damage. Thank you.
フクバイさん、どうもありがとうございました。今、示していただいた、 非常に低線量なんだけれども健康影響が
In low
ある
doses,
と
there
いう
is definitely a health effect, or at least there appears to be a health effect based on how this data has been extrapolated. And I believe that there's a lot that can be inferred from this. There is very little similar research like this in Japan. So from an epidemiological perspective, I think there's a lot for us to learn in terms of how to do this type of work. Now, still in the field of epidemiology, in Japan we have a leading expert, especially in the area of thyroid. And Professor Tsuda has spoken at an experts panel at the Environment Ministry, so we will turn it over to him.
Very much for the introduction. What I am focused on is to prove that under 100 millisievert no cancer. I like to prove that that is a lie, and that is what I'm focused on. Also, of course, this is not an issue that I've been focusing on, and also this content of the publication has already been featured in the Kagaku Science magazine October edition, and I'm just copying what I had written on that publication. So I'm just gonna move very quickly through pages, and what's really important is at the very end. Am I supposed to conduct myself? Okay. Well, because I am very polite, I would like to first of all express my gratitude to all the speakers who are present here. Since I am from Okayama, I kind of feel that the environment is very different in Tokyo, because in Okayama, people have forgotten about March 11th. And actually, very few people in Okayama know that I talk about this issue or I write about this issue. And that is why, especially, I am grateful that the people, especially from abroad, are interested about the situation here in Japan. So I'd like to thank you. And I especially am grateful of the content in the presentation from the German chapter of IPPNW, because it was extremely helpful. We in Japan, especially in Western Japan, where we have kind of forgotten about the situation, we will keep trying our best to make an appeal to the international countries. And this page actually was covered earlier. We talked about it last year as well. And this is where the earthquake occurred, and this was the actual maximum peak. And then actually, it was recently reported that right after the accident in March, we had quite a high peak as well. And this is the movement of the plume after March 11th onto 12th, 15th, and 20th, and 21st, where it has been spread. And actually, it's quite recently that the newspaper reported wider spread, and that was differing from my previous understanding that the 15th was the largest spread of the plume. That was not the case. And now, when it comes to the thyroid cancer, as I have repeated numerous times in different places, we have the precedents in Chernobyl, where for Chernobyl they didn't have any precedent, historic precedent. So we need to learn from Chernobyl's data. And so horizontal time and vertical axis, the number of cases. If you look at this, and if you compare our situation to what had happened post Chernobyl, we understand and we can get a lot of information in a chronological manner, including what will happen. So Fukushima is equivalent. Where we are now equivalent to here, post March 11th. If you look at the Chernobyl data, and you can see that there is a clear and evident increase in the cases of thyroid cancer. Are we going to ignore this, or are we looking at it? That is really a big difference and opinions among the experts and scientists who consider that this is a massive increase. That's a normal way of looking at this data. Well, scientific curve, such as this indicates that if we can see this kind of curve, then an ordinary curve is a more general distribution, where the curve is more of a gradual increase rather than such a sudden peaking. So, as a very basic discussion, such basic discussion is basically non-existent or is missing, and that is the current issue. Why do we look at the thyroid cancer data? Well, because it's the public interest, because predicting, grasping the spread as well as the extent of the outbreak in the future is important. We need to look at the future and forecast of the future. Chronological understanding, and we also want to separate the effect of air dose rate and iodine 131 because we have the shortage of information regarding iodine 131. And also, if we could undertake reverse estimation of the exposure dose or air dose in that time, looking at from the incident rate, that's what we would like to do, and that's what I already talked about. And now, the impact of iodine 131. Well, there is quite a lot of uncertainties in terms of the air dose. So, in a way, we can look at the young population who is more sensitive to iodine 131 in order to understand the overall air dose rate. So that's a biological monitoring that I'm talking about. Now, thyroid cancer screening for ages under 18 years old, and this is the schedule, of the thyroid cancer screening that you all very well know that is being conducted year 1, year 2, year 3, and this is the mapping of the order of the first round of thyroid cancer screening in year 1, 2, 3. But you have to understand that the population density of Fukushima Prefecture is about 3 times higher than that of Gomel in the Republic of Belarus. The pink area here will undertake the test in the first year, yellow second, and bluish color third year. So these are even color coded. And so I'm presenting the information in a more easy to understand manner compared to last year. Now, external comparison. We were comparing the data between the Center for Cancer Control and Information Services of the National Cancer Center and the Fukushima's information within Fukushima. And the age group here is 0 to 19, but if you look at 0 to 19, it will be only 2 or 3 people in 1 million people. That is will be very low, but I'm taking a 5 in 1 million as a slightly higher. People misunderstand that actually I tend to take always a bigger figure or higher figure, but that's not the case. I always take the lower figure, almost infringing my thinking as a scientist, and so. But I'm always trying to take the lower figure, but still. If you look at the external comparison, when adjustment and estimation. So now we have to first define the prevalence, which is incident rate multiplied by average disease duration. And incidental rate, which is an epidemiological theory. And also several disease durations scenarios were assumed for sensitive analysis. So it could be from 1 year to it could be even as long as 100 years, and it's quite easy to take this duration using an Excel file. And Poisson distribution was employed to estimate 95% confidence intervals. Now, internal comparison in regional divisions. So within Fukushima, we have created 6 distinct regions as indicated by the color coding earlier. So these are the 6 regions. Yes? And first of all, we have the first round that is completed in 3 years. So this is the total data of the initial first round, first 3 years. So till November. So and this data actually is available through the website of Fukushima Prefectural Government, or you can also buy the Kagaku magazine by the Iwanami publisher. So please buy the magazine. And if there is anyone from Iwanami, I'd like to ask you to raise my salary. Now, this is the thyroid cancer in Chernobyl. In 1986, the accident occurred, and you will see the incident rate as you can see here. The horizontal axis is the age as of 1986, and you can. So this chart basically demonstrates whether there is an impact of the accident or not. So from the very young age, well, the reason why that in Japan, the experts or the government claim that there is no impact of the Fukushima accident in the increase of the thyroid cancer is that they're seeing a very young incidences. But looking at this thyroid cancer in Chernobyl data that is created by Professor Yamashita, you can see that even at younger age you see the incidences. So in that sense, there is a similarity between Chernobyl and Fukushima. And this is the result of Nakadori in 2012. For cancer, so actually, this is a result of the fine needle aspiration screening. And this is the number of the detection of a cancer cells. And you can see that basically there is no difference. So it's basically 98% commonality. So you can see that you can undertake a fine needle aspiration for quite a reliable data. This one here was Nakadori, and this is the result number 3 of Aizu and Hamadori. The total target was 40,000 people, I believe. And that's why they decided to undertake the test for Aizu and Hamadori together because of the relatively lower population. And here, this is the table for external comparison, which is a comparison between Fukushima and all of the rest of Japan. And you can see that the prevalence rate is, as you can see here. So on the very highest region, its incidence rate ratio is 22.32%. The north part is 15.79 within the 95% confidence interval. And you can see that for Soma area it's basically 0, but then for all the rest of the areas there is actually a noticeable percentage. When you look at the comparison within Fukushima Prefecture, this is an internal comparison. We are comparing the prevalence odds ratio with Aizu region, which is quite low. Of course, the lowest level would be Soma region, but this is 0, so it would not be a very good comparison target. So we decided to compare against Aizu. Naka area is 2.19, so forth. Furthermore, this one here is the adjusted prevalence rate. And here again, we have seen the incident rate ratio, and also we have seen we are showing how many people within the entire target population. So the lowest is about 1 in 1,651. That is in Naka area. When you can see that in all of these areas that are indicated on this table, you can see that the prevalence ratio is higher in all of these cases. So you need to show the actual figures to show clearly the situation. But however, the government authorities never quote actual numbers in a quantifiable manner. They always say there's no impact, there's no measurable impact, etc., etc. But the basic of science that you always give the numbers.
で、数字にする方法は教科書に載ってる方法にのっとったやつがあるんですね。
To follow the textbook to calculate the quantified number, and you see the quite a number of differences. For example, if it's more than tenfold, it's quite a lot of significance. And now there is no boundary between the prefectures. For instance, if you look at the southern part and the northern part, we have to capture the actual cases, and I'd like to elaborate on that in the latter part of my presentation. At any rate, if you get on the Tohoku Shinkansen bullet train to get to the Fukushima, I did it to see what happened in Fukushima, and I said Fukushima is such a great place to see such the idyllic scenery, and another person happened to sit to me said that no, it's totally different from Chernobyl. First of all, population density is totally different between Fukushima and Chernobyl. That person knew that Chernobyl, if the density is high, even though the release level is the same, the prevalence rate will be higher for carcinogens or cancers. Now, you see, year by year, although it's very small, but there is a gradual increase. And you see, year in and year out, there's an increase steadily. The first screening, the first in the area, is more handicapped, and if you handicap adjusted, you see, the closer the area is, the higher the IRR is. So if you manipulate numbers, there are people who criticize you or your analysis. Therefore, this is just a reference because the second round survey will happen. Therefore, it's serving as just a reference number. Now, this is based on the data prepared by Dr. Imanaka. And as you can see here, after 1986, you see the increased trend. This is focusing on the pediatric cancers, and I have presented this already in last year. And starting in 1986, steadily, though it may small, but the cancer incident or cancer cases count has increased. For example, the small scale unit is 100, and then on this graph, 100 is here. That means that if you superimpose these two graphs, you see the small increase. Therefore, rather than the younger than 18 years old, the ratio is very small. However, actually you will see the higher number of patients in the population older than 90 years old, and you have to clearly understand it. And actually, it is said that it's a first attempt by conducting such a large-scale screening, according to doctors in Fukushima University and Nagasaki University, but it's a total lie because there's quite a number of screening conducted. However, age population is different. In case of Fukushima Prefecture, age bracket is by far wider than the other studies. And still, we see the higher number of cases. And of course, if you look at the three prefecture study, age is higher. Still, we see the higher incidence of cancer. In addition to that, if you look at the person distributions, and if you go to the university, you may know what the person distribution means. And if you learn the statistics, you know what it is. One case and 11 cases and 21 cases and 20 cases are totally different because the distribution range is narrower and narrower. Rather than distribution, the standard of error comes smaller and smaller, Therefore, the fact that one case is detected on one hand and the detection of 23 cases or 11 cases, these two are totally different. And the problem is that there is no argument at all and there's no explanation for these differences between one case detection and 11 case detection and 23 case detection. And actually, the non-exposure population is the subject of many studies in Chernobyl. This is the three studies supported by these three papers. And by the way, if you look at the March issue of Iwanami, you can see the details. And you have to buy the March issue of Iwanami, then I get a more copyright fee. By the way, this is emphasized by the doctor in the non-exposed area. Back then, there's no fetus actually. The in the non-exposed areas, they were studied, and the total number is 70,445, and only one was detected of developing thyroid cancer by utilizing the same echographic screening method. Less than 300,000 people were subjected to the study in our case in that area. 4 or 5 people at most were detected to have the thyroid cancer, and Dr. Yamashita seems to know it. And his explanation is that in the first round of screening, 5 people would be detected of having thyroid cancer, and right now 104 or 103, excluding a certain type of benign cancers, the 104 was detected compared to the originally predicted 5, meaning that there is a high precedence or the high incident rate of the thyroid cancer. This is really clear-cut data, no argument at all. And then the problem is that nobody takes a look at this because there is the lie that the radiation dose below 100 millisievert does not cause cancers. And then in the Belarus and Ukraine, there is a clear increase of thyroid cancers after Chernobyl. And back then there was no screening available. Still, this number of people was detected as having the cancers. However, before Chernobyl, there was almost no thyroid cancer, and the CDC. By the way, this building has come to be really popular thanks to the Ebola fever. At any rate, the CDC said that the minimum latent period of thyroid cancer is 2.5 years and 1 year for the adult and the child, respectively. And at least several years are necessary for the thyroid cancer to develop, and in some cases 10 years are necessary. However, this is mean value or median. However, what we are looking at is a minimum latency. It's not mean latency. Therefore, you should not be duped by this number. So we are talking about the minimum latency rather than the median or mean latency period. Now, based on the experiences and expertises we have captured in Chernobyl, just 3.5 years have passed, and we have to brace for the huge peak of the thyroid cancers, and we have to develop a screening system as well as the infrastructure to deal with potential cancer cases, and especially the subjects who were older than 90 years old when 3/11 happened. We have to cover them as a screening subject for thyroid cancer, and we have to establish a good system for non-Fukushima people, and I believe this system could be established immediately. However, there's no such system in place yet now. The fact that the epidemic of thyroid cancers were higher than anybody's expectations. In addition to the iodine, we have to consider the aerial dose as well as the other radioactive nuclides. Therefore, in the higher order or in the important order of pregnant women, infant, and so on and so forth, we have to prepare the good screening system. And then this is when the peak happened, and Fukushima is in here, and we have to brace for this situation. And actually, there's nothing prepared. Just for your information, if you look at the report by the WHO, It's said that the cancer is not caused by the dose level below 100 millisievert, and it's totally lie. You can cite by taking a look at this, and the problem is that the WHO report is not communicated to the Japanese public at all, and this blue part shows the increment due to the Chernobyl accident, and the gray part is the leukemia caused by the background radiation, and the 1-year-old, 10-year-old, 20-year-old as of the accident was the subject of the study, and the WHO clearly shows that there is an increase due to the accident. So the takeaway message is that it's wrong to say that the exposure less than 100 millisievert does not cause cancer or not known. It's totally wrong. WHO predicts that because of the exposure and the prefecture of Fukushima, there will be an increase in such cases as thyroid cancer, leukemia, breast cancer, and other solid cancers. The WHO says it, therefore, if anyone say that there is no such thing will happen, it's meaningless. However, the problem is that it's not known to the general public, and the overseas researchers don't know that the Japanese public has not communicated about this fact, and this is a really appalling fact, really jaw-dropping fact, that this very important fact is not well communicated to the general public of Japan. And I have to emphasize these 2 points, especially the emphasis on the expected increase of thyroid cancer. For example, IOD-131 maybe is the only one culprit in your mind to cause thyroid cancer. However, actually, the external exposure is another source of, or another cause of thyroid cancer. As to the thyroid cancer, this blue part is an increment part, and compared to when the accident did not happen, it's clearly higher. So this much increment is expected, and we can identify who develop the thyroid cancer after the exposure. We can clearly identify who to develop. Dr. Tanioka said that we cannot scientifically determine who developed thyroid cancer due to the accident. This is a remark of Dr. Tanioka. So the syntax or the common language of the science is a probability. Therefore, if the person says the definitive number, absolute number, he or she does not know the science. Everyone believes that Japan is a science-based or science-oriented nation, but it's not the case. Especially, I want to ask the German person to listen to this. Japan and other people believe that Japan is a science-oriented nation, and all of the public institutions, including the schools, get the payment because they teach science. However, if you ask what science is to a teacher, nobody would be able to answer to that because nobody has given a thought about what science is. That is the situation of Japan. Now, this is based on the data issued by WHO, as you can see here in the pediatric patients. You see the year by year increase. And then if you compare gray part and blue area, the ratio between them, the blue area is overwhelmingly bigger, meaning that in all of the age populations, we will see more cancers. In addition to that, it to be more conspicuous among pediatric cancer patients. It's undeniable fact. Last year, around the same time of the year, I said, despite if you want to betray the general public, only the potential measures to betray public is the data falsification. That's what I said last year. I am a servant to the administrative office. Therefore, I have to fulfill the interests of the government and administrative offices. You may have an opposite view, however, I'm on the side of administrative offices and I'm on the side of the government of Japan. But I have to say to the government of Japan that they shouldn't stretch themselves too much because the causality can be observed, the diseases can be observed. However, you cannot clearly see the causality because you cannot see it, you cannot listen to it, you cannot taste it, there is no odor, it's untouchable. Then the sixth sense is the only one thing you can rely on to say that causality cannot be directly observed. And that's what the Fukushima Prefectural Medical School says it. Prediction based on the observational data is the basic for the science in order to visualize causality. That's why we use the hazard ratio, risk ratio to visualize the causality in numbers, and this is what the epidemiologist has to do. Then, in the real world, whether there is a disease or not, or whether the person develops a disease or not, and when that person was there, these can be described in numbers. Thus, it's not clear. Therefore, we use the years or period of residence as the compensating number, and we analyze these numbers, and then on the right hand side, you deduce the general principle, and that is the basis. And then in epidemiology, odds ratio and incidence ratio are the common language to describe this. However, on each one of the phenomena, you use the data in the Excel spreadsheet, and the cells in the spreadsheet tells you the numbers, alphabetic numbers. However, this entails the probability distribution. And if you take it as a peak, that's why science is really sharp. Because you pick up only the peak here, that's why it seems so sharp. And because you take a look at only the peak area of distribution, that's why you have a higher probability. However, you should not forget that there is a trails in the normal distribution. Therefore, the data-based probability theory should be presented, and if the person does not do it, you should not believe in that person. That person is not a scientific person. So whether that person uses this data, including the distribution, you yourself whether the doctors from Fukushima University or the Nagasaki University do this, you can tell whether that person is based on science. And this is the period prediction, and the 95 CI is here. On the x-axis, you see the odds ratio, and on the y-axis, you see the probability. Odds ratio is in rate, does not take negative numbers, therefore you have to take the log number. Opposite log number, it's like a Poisson distribution. That's all for me.
からできてよかったと思います。以上で理科の先生の講演を終わりたいと思います。どうも。
津田さんどうもありがとうございました。今100ミリシーベルト以下影響ないというその影響がほとんど見られないというその言い方に対してですね、津田先生冒頭でですね、私は全然力をつけているとおっしゃいましたけども、実はこの最後のスピーカーである非正バストさんですね、その問題をアンケアの告知にも焦点を当てながらお伝えください。ベーバストさんは皆さんもご記憶の方いらっしゃると思いますけども、昨年もこのシンポジウムに参加されまして、エピジェネティクスという生物学の新しい概念ですけど、それを捉えながらですね、生成療法学をどういうふうに新しく見ることができるかという話をしてください。よろしくお願いします。
your kind introduction, and I would like to. Thank you, Mr. Chairman, for the kind introduction, and I would like to thank the organisers for the invitation to come and talk to you on this very critical issue of the effects, the potential health effects at doses of less than 100 millisieverts. This is a particular feature of this accident because actually I don't think that this has been particularly developed in any other earlier event. So this is a new feature to in radiological protection to try and impose some kind of threshold. And we see it here in the proceedings of the Oversight Committee for the Fukushima Health Management Survey. It states that the latest effective radiation dose estimates show similar trends to those of the past. Previous epidemiological studies indicate no significant health effects at doses of less than 100 health effects at doses less than 100 millisieverts. Is this scientifically credible? They lean on a statement in a previous report by Unskier in 2008, and they cite this in support of what they've said. So far, neither the most informative LSS study, that's the lifespan study, and atomic bomb survivors, nor any other studies have provided conclusive evidence of carcinogenic effects of radiation at smaller than 100 millisievert doses. And so the issue here is, what do they mean when they say conclusive? Because actually epidemiology, as somebody else has already said, cannot give you conclusive results. They can only give you a statistical probability, a probability that the increase or whatever you are observing is significant at some level. And typically, for epidemiological studies in radiological protection, we use what's called the 95% confidence level. That is that only 1 out of 20 times would we expect the result that we get to be a chance result. So we can look at this to understand how this concept works at tossing a coin to see whether the coin is biased to land on one side, and I've chosen heads up. And I've got a little experiment that we do. We toss the coin once, it lands heads up. We toss the coin twice, it lands up twice, heads up. When we have tossed it 10 times, we find that 7 cases out of the 10, it's landed heads up. And when we toss it 50 times, it's heads up 30 of those tosses. And when we do it 100 times, it's 61. Now, let's look as if there's any relationship between the number of tosses and the number of heads up, and in fact, it's a statistical thing, it's chance. And the question that we want to ask here is this coin that we've notionally tossed in this thought experiment, is this coin biased or not? When can we say that we shouldn't use it to get a random distribution, if you like, to call heads 1 and tails 0, and we want to get a row of randomly distributed noughts and ones, could we use this coin for that, or would it be biased, producing more ones than noughts over a very long term? And so we can calculate what's called the p-value. Well, it's meaningless for one toss, but for 2, the p-value here is 0.25. For 10 tosses, 7 heads, it's 0.117. For 50 tosses, with 30 heads, it's 0.042. Now it has crossed the 95% confidence boundary.
This value here is less than 5%. And when we go on for the 100 tosses, it's quite clearly 99% certain that this coin is biased to land heads up. Now, when we're looking at the effects of radiation in a population, we're doing very much the same thing. We are looking to see if the general population that's been exposed to radiation is showing more disease
than a population, similarly drawn population, the same number approximately of people, the same proportion of males and females, the age distribution is similar. Then we are looking to see if we can see a difference between the exposed population and the non-exposed population. The non-exposed population we call the control group. So we're comparing the exposed group with the control group, and we're looking to see if we can see a difference in the two populations. So we're going to use the 95% confidence interval, because you can see that we have to increase the number of tosses of that coin quite dramatically in order to get improvements in the result. So we must assume that unclear means by conclusive means 95% confidence. And unclear admits quite freely that above 100 millisieverts, there's plenty of evidence at confidence intervals greater than 95%. That there are studies which demonstrate risk. And we have many of them. The question is, do we have any below, doses below 100 millisieverts? Because if we do, then unclear is wrong. Unclear has misrepresented the information. So there is one important point to note, and that is that the size of the population is very important. So if you have a group, let's say, of 1,000 people, and they're exposed to a relatively low dose of radiation, you will have considerable difficulty in seeing an effect at 95% confidence. If you had 10,000 people with the same dose, you have a much greater chance of seeing the effect. And it's possible, because statistics is a regular subject, you can calculate what the statistical power of a population will be, and you can say rather clearly whether you would expect to find an effect on the basis of current knowledge about the relationship between dose and effect. Of course, if your population is going to tell you something new, that for example, they are more sensitive than you thought to radiation, then that calculation is somewhat inevitable. But I just want you to take on board that increasing the number of people in the population that you study makes it easier to detect a risk. And therefore, studies with a significance of over 95% at doses less than 100 millisieverts are at least as reliable as those above. So there is nothing magic about this 100 millisieverts, but we will come to see why it is used. So it has no special significance. It's false to assume it does. And UNSIA is actually misleading, deliberately misleading, in claiming that there might be a difference. And you notice that they use this word inclusive without really defining what they mean. We know they don't mean 100%. So this is what we call a weasel word. A word that is put in there in order to distract your attention. Somebody earlier today spoke about the power of language. Well, you'll see it there. So let's see. We've already heard about from Dr. Rosen about the study by Dr. Alan Stewart of children, pregnant women given X-rays back in the 1950s, 1960s. So it's a very old study. And there are in fact 8,500 cases of leukemia were compared with a similar number of controls. That is, women who didn't have X-ray diagnosis during their pregnancy. And the relative risk comes out in that study to be 1.47 for childhood leukemia in the children born from women who received the X-rays. And that is significant at the 95% confidence interval. And that's just based on the number of films. Sometimes they took 2 films, sometimes just 1. But if you analyze it, again, in terms of the number of films, you can see that that figure, 1.47, is actually related to the number of films and therefore to the dose. So it is dose dependent. So we know there with a high degree of confidence that it is the radiation that is causing the same. Now actually, the level of dose is less than 10 milligram at which the cancers are induced. And that is more or less the lowest dose you can give to a single cell. Because either the cell gets an electron passing through it, and if it does, it's getting a dose of around 10 milligray, or it doesn't get an electron going through it, and then it doesn't get any dose at all. So actually, we can't really talk about a threshold less than 10 millisievert, because it's just the physics does not allow you to have doses of 2 or 3 millisieverts. Now these results caused huge controversy at the time. Nobody wanted to believe that you could damage the health of a baby by irradiating its mother with something as considered to be very safe, a single X-ray. And the results have been extensively debated and reanalyzed, and the conclusion remains the same today as it was on the first analysis. And just as an aside, here it's interesting to mention this study, this KIK study. It's called KIKK study in Germany, looking at the distribution of leukemia cases around nuclear power plants within 5 kilometers. And there is a significant increase in leukemia in children, which Ian Fairley believes is the result of irradiation of mothers, pregnant women, due to releases of radioactivity into the air during the changing of fuel rods and the maintenance procedures. This is an ongoing issue. It will be investigated even further. But the point is that these doses cannot be very high because there is no clear measurement of or gradient of dose with distance to the power station. But it seems that these doses can be of only a few millisievert. Now, it's not just children, because adults are also known to be sensitive to radiation at doses below 100 millisievert. And this study has also been referred to today. This is a study conducted by Dr. Cardis of more than 400,000 radiation workers. And the reason for the controversy when that paper was published in the BMJ was that this figure, 1.97, this risk ratio, was statistically significant at the 95% confidence level. And nobody wanted to believe that either, because the average cumulative dose for these workers was only 20 millisieverts. So this is in contrast to the Japanese bomb survivor studies, where the doses ranged up to 2 gray, where in the region where we can measure the risk. And that central estimate was about 1.4, also significant at the 95% level. But the average doses are more like 100 millisievert. So the fact is those radiation workers, the average doses for the Japanese bomb survivors are higher than that. So this central estimate of 1.97 is, of course, higher than the 1.4, and it doesn't indicate conclusively, that is within the 95% confidence intervals, that low dose rate radiation is more damaging than high dose rate radiation, which we thought was the other way around. For many, many years, we assumed that at low dose rate, we could actually apply a factor 2 to, you could have twice as much at the low dose rate to get the same effect as at the high dose rate. And now it looks like it's the other way around. It's not going to be a factor 2, but it is possibly a bit more dangerous to be exposed at a low dose rate compared to a high dose rate. And of course, it's the Fukushima exposure is at the low dose rate, people living in contaminated areas. And finally, there's a growing body of evidence that ordinary diagnostic X-rays, and that includes CT scans, but not exclusively CT scans, is showing excess risks. So we are starting to be able to measure these risks at very low exposures as we build up larger and larger populations. And so the idea that there are lower risks per millisievert or per 100 millisieverts at doses below 100 millisieverts is simply shown to be false by the evidence. We don't need the theory, we just need the evidence, and we have that evidence. And there is more. I'm not going to go through it in detail now. A paper is in preparation, and we are hoping to get it accepted, but it's been turned down by at least one journal. But what I want to point out is that this is not new. Possibly you can't read this list of authors here, but these are the great and the good of radiobiology in approximately 2003, I think, or 2002. And they pointed out that if you look at the data on the atomic bomb survivors, and we see it here, the doses in millisieverts up to 400 millisieverts, coming down to close to 0. And this dotted line is the extrapolated line linearly from 2 gray, so 2000 millisieverts, and we look down at this end and we see that the majority of the spot points where you can make those kind of estimates lie above that line, which suggests that the risk at low dose could be higher than the average risk determined, that figure we saw of 1.4, the average risk determined from the whole atomic bomb survivor population. So this was current in 2003, was published in PNAS, Proceedings of the National Academy of Sciences, a very reputable journal, and therefore I think it's not in any way new to accept that these risks exist at doses of less than 100 millisieverts. Now the important benchmark here is 20 millisieverts per year, as that is the level at which people might well be expected to live. External exposure of 20 millisieverts per year. So I want to just look what this means in terms of risks. And the first thing that we need to consider is the dose rate in subsequent years after the accident. So when the accident took place, if you found an area that was 20 millisieverts per year immediately after the accident, it will have dropped by a factor 10 a year on. And that's due to the decay of the fresh, short-lived radioisotopes. If you go now to 3 or 4 years after the accident, and you take a place which is 20 millisieverts per year, the drop over that period of I think it was actually, sorry, it's 10 years. The drop over 10 years will not be anything like that. It'll be down by a factor of about 2. So we'll assume a factor 2. It would vary from place to place, or rather more from time to time. And we'll use the data from the Beer Committee of 2007, Beer 7, that was also mentioned today. And I think this is the most solid data on risk that we have. And you can see here the age against the number of cases per 100,000 exposed people. And you can see how the risk increases for young people dramatically, and for females much faster than for males. And I'm going to take a worst case scenario, if you like, by taking the example of a female. This figure, DDRF, UNSCEAR, I mean, I think many people have thought that the DDRF of 1 rather than 2, which I mentioned earlier, should be used. And UNSCEAR actually, in their latest report, does use 1, or recommends the use of 1. Perhaps one of the good points that they've made. So in this worst case scenario, I'm going to look at a girl, 1 year of age, and then introduced into an environment giving 20 millisieverts per year and dropping to 10 millisieverts per year after 10 years, an average dose rate of 15 millisieverts per year. And so she's going to get, over that period, 150 millisieverts, and her lifetime cancer risk for that 150 millisieverts will turn out to be 6.75% by using that graph that I showed you on the previous slide. And in addition, there could be a further risk of non-cancer disease, which is much more difficult to quantify, but it could well be of a similar magnitude. So within the first 11 years of her life, she could have incurred a risk of serious disease within her lifetime of some 10 to 15%, which is very rough figures. So we won't be concerned with decimal places. Now if we compare that with the lifetime risk to a male radiation worker working from age 20 to 60 years and receiving the maximum allowable dose under the ICRP limits of 5 millisievert per year, giving him a lifetime dose of 200 millisieverts. And this is a quite feasible scenario for a radiation worker at Fukushima over the next few decades. So from the previous graph, we see that his risk accrued over those 40 years is roughly 2% for the 200 millisieverts. And we could double that to allow for non-cancer disease. That's just a rough estimate. So 4% of serious disease for a lifetime of radiation work. Now, we could also look at the case of a girl, a 1-year-old girl, living for 10 years in a non-contaminated region and just receiving natural background radiation plus 1 millisievert per year of public dose. Oh, sorry, I'm told the time is over. I'll be very quick. So if we look at her risk, it's 2 to 3%, and that would imply more or less everywhere in the world. So we saw that the effects were observable down to 10 millisievert, and so that's a reasonable estimate of risk. Now, what would be the effect of assuming this 100 millisievert threshold? So we would see that the girl living in the contaminated area would get a 2 to 3% risk if you neglected everything below 100 millisievert. The radiation worker would end up with 2% total risk, and the girl living in the non-contaminated area, 0 risk. So, I will end now. I'm just pointing out that I've only taken in so, yeah, I'll leave that point. So the conclusion is that it is not sustainable scientifically to assume that the risk will be lower at below 100 millisievert. And almost certainly the risk is linearly dependent on dose down to 0, in other words, LNT. But now, 3.5 years after the accident, we don't have a detailed picture of the risks that are involved to the population from this accident. Thank you.
デイバーストックさん、どうもありがとうございました。それでは残りの時間そんなにないんですけれども、質問をですね、今いくつか集まっておりますので、まだ出してない方は今出していただけるとありがたいです。で、科学的な事実の確認というあたりから入っていきたいと思いますので、あと2、30分ちょっと、お付き合いください。一つはですね、古久林さんに、まず、質問なんですけどもよろしいですか。データの中で、胎児の女の子の死産が多いというのがありました。なぜ女の子なのでしょうか。理由が推測できるのであれば教えてください。
Die Mädchen sind bei eisengenetischen Fragen the girls are for all genetic Probleme empfindlicher als die Jungen.
影響を受けやすい遺伝的な問題に関しては女の子というのがどんな時でも男の子よりも影響を受けやすいということがあります。
Vielleicht liegt das daran, dass die Mädchen vom Vater das X-Chromosom geerbt haben und das X-Chromosom empfindlicher ist.
X クロモゾームを受け継いでいるので、それの方が影響を受けやすいということがあるのかもしれません。
Aber genauer kann ich das nicht sagen.
でもそれ以上詳しいことは私にも分かります。
はい、わかりました。じゃあその次移りたいと思います。実は、はい、そうですか。はい、ローゼンさんよろしいでしょうか。大丈夫ですか。はい、こんにちは。
2つ質問があります。一つは、バックグラウンドの放射線とフォールアウトの放射線の影響の仕方が異なるというお話がありましたけれども、それをもう少しどういうふうに異なるかを教えていただけませんか。
I only got the Japanese, I did not get the English translation. Sorry.
通訳の人、英語が聞こえてないようなんです。
Question was, what is the difference between background radiation and the fallout radiation? How do they affect humans differently?
In general, there is no difference between different types of radiation as long as the dose, the effective dose to one individual is the same. So 1 millisievert of background radiation or 1 millisievert of radiation from man-made sources like fallout or like medical radiation should be the same on tissue. But, of course, there is a difference when you talk about fallout radiation that you ingest with the food as opposed to cosmic radiation, which comes from space, or terrestrial radiation, which comes from the ground. Because obviously your skin protects you from some level of radiation, and especially your inner organs, whereas the radiation you take in with the food that comes into your body poses a larger threat to your internal organs.
よろしいでしょうか。じゃあもう一つあります。内部爆の計測に関してです。今から内部爆を計測するとすれば必要な手段は何でしょうか。
If we wanted to take measurements of internal radiation now, at this point, what kind of methods are available to us?
It's very difficult to measure internal radiation in a living being. For a fruit or a vegetable, you can take it, you can cut it into very small pieces, put it into a machine, and measure the radiation or the radioisotopes that you actually find in there. In a living being, the only thing you can do is measure the radiation that the body emits, that the body sends out. And obviously, there you can only measure gamma, and in certain cases when it's radiation on the skin, beta radiation. Alpha radiation you cannot measure with a whole body counter. So you need calculations to adjust, for example, if you measure a certain type of gamma radiation, you need to then calculate, if you know which isotope it is, how large the beta or the alpha component of that would be. So it's always a lot of guesswork, and it is always a singular measurement. You are measuring the amount of radiation in that single moment. What you cannot say is how much of this radioactive material was in the body 1 week ago or 1 month ago. Because you don't know, for example, if the radioactivity that the body emits now is from a radioactive contamination yesterday, meaning you took in a small amount of cesium yesterday, which you can now measure, or whether it is a leftover of a very large amount of cesium that you took in 1 year ago. And now it's deteriorated to only this amount of cesium. So it's a singular measurement that does not tell you anything about the effective dose over a large amount of time. You would have to measure the same person in separate incidences over time in order to really make an educated guess about how much radioactivity, internal radioactivity, the body was exposed to, and could only get a certain amount of radioisotopes.
それでは科学的な質問ということで、今度は甲状腺のことがたくさん来てるんですけれども、いくつか選んでお聞きしたいと思います。津田さんにお願いしたいんですけれども、甲状腺がんの発症が、いわゆるスクリーニング効果というふうに説明されることが多いのですが、それについてはどう考えていますか。話は説明したように、スクリーニングによって非暴露地域で見つかる甲状腺がんの頻度をお示ししました。チェルノブイリ周辺で非暴露者だったと思われる人たちの中では7万人に1人しか見つかってません。そういうもの同士、そういうデータがないというふうに宣伝されているわけですか。そういうデータがあるんです。それと比較した場合、桁違いに多いんですね。で、スクリーン効果と言われる人たちはこう言い返せばいいです。スクリーニング効果というのは何倍ぐらいの見せかけの多発を起こす効果ですか。論文でお示しください。スクリーン効果というのは安易に理由で示す人たちはスクリーン効果に関する論文を読んだことないんです。でもあるんです。甲状腺がん以外のがんでもあるんですね。で、甲状腺がんでもさっき示したようにあれスクリーン効果込み込みで7万人に1人です。チェルノブイリ州では。で、あれに対して、何ていうかと言いますと、1990年代半ばとか2000年頃の検査なので、今の高精度の超音波エコーよりは、性能が悪かったというふうに言うわけですね。でも今B 判定に回されて、精密検査に回される人は、結節で 5.1 ミリ以上、脳胞で20.1ミリ以上ですね。私は1980年代後半に、内科医としてエコー検査をやりまくっていました。それで肩が凝って嫌になって、やめましたけども、ものすごい数やってましたけど、当時のエコーででも5ミリぐらいの検出能力はありましてですね。ましてや1990年代半ばとか2000年代にはもうそんなもん十分に検出できる能力があるわけです。もし、それが検出できなかったエコーでやってたというふうに言うのであれば、1980年代前半、エコーが養分探知機から人間に応用されだした頃の超中古品をロシアに行って、やったというもしそれを売りつけてたとしたら、それはやっぱり山下先生たちがちょっと悪いことしたんじゃないかということになりますので、そこそこの中古品程度を持っていっていれば、そのくらいは検出できないぞということになります。はい、続きまして、最近の、報道で県立医大の鈴木真一教授が甲状腺学会で、今見られる福島で子どもたちが発症した甲状腺がんのがん細胞を調べたところ、遺伝子の変異を解析したと。その時にその方が 遺伝子の解析の結果分かった方が遺伝子の方々、チェルノブイリ型とは違うということを見つけた。したがいまして、原発の影響でこの甲状腺がんが起こったとは思えないという結論を、示されたようなんですけれども、それに対してはどう思いますかということで、津田さんとそれからレーバーストックさんのお二人に質問されています。じゃあ津田さんからお願いします。
いつもの通り形容詞の羅列です。数字では決して示さないんです。違うと言っても12と13も違うし、1と13も違うんですよね。一切データを示さないんです。
How about Keith?
I'm not sure that I got the question very clear. Can you repeat the question?
質問もお願いします。はい。質問をもう一度お願いします。質問をもう一度お願いします。
それ根拠を示せ、データを示せというのは福島のデータとチェルノブイリのデータ両方示す必要があるんです。どちらも示せないんです。何人か福島だけ示せないんです。チェルノブイリと比較して違うと言ってるんで、それ示せないんです。で、サンプルサイズとかそういうのもチェルノブイリの側も示さないんです。それ示せないんですよね。そもそも1対1対応するものがないんです。病気と暴露と原因と結果、要するに病気とは一対一関係しないんです。これが自然科学の原則なんですね、因果関係。で、そこのとこ分かってないです。遺伝子まで見れば確定的影響が見えるかもしれない。でもそれはちょっと違うように見えるというふうに言えば因果関係否定したことになると思うんです。鈴木先生は自然科学、科学とは何ですかとまず研究する必要がありますね。で、現代の因果関係論について全く知識がない人ですから、それもしょうがないんです。そういう形容詞だらけのお話になる。それともう一つ、タバコと肺がんを否定するためにね、昔もあったんです。クライベルグ仮説というのがあったんですね。タバコによって起こる肺がんというのは、扁平上皮がんと当時は遺伝子までいきませんので、扁平上皮がんと小細胞がん、タバコ、したがってそれ以外の肺がんが大細胞がんと腺がんというのはタバコとは関係ないという話に持っていかれてます。でも今、いずれの方とも関係するということになっておりまして、その種の小さく分ければ何か因果関係が分かるという理解というのは常に裏切られているんですね。
それではもう一度、短く質問いたします。福島の子どもたちで発症した甲状腺がんの
The thyroid cancer that was caused to children in Fukushima, well, they have undertaken a study on the cell level, and they looked at the form and shape of the DNA in Fukushima, and they detected that that form was different from that which was detected in Chernobyl. And based on that, they are saying that the incidence of thyroid cancer in Fukushima is not caused by the nuclear power plant accident. Can we really say that?
No, can't. Actually, it's not possible to tell anything about the origin of thyroid cancer from looking at the DNA. Many people thought that was a huge opportunity when the thyroid cancers occurred after Chernobyl, because particularly in young children, the chances that you actually had a child with radiation-induced cancer was very high, perhaps up to 90%. And in most cases, when you have a cancer in a population exposed to radiation, you don't know to better than 20% whether that person might be radiation-induced cancer. So they had the opportunity to examine thyroid cancers in great detail, look at molecular structures, to look at the rate at which genes were being expressed, and all sorts of factors like that. Huge amount of work is done. And to my knowledge, unless it's happened in the last few months, there isn't a single case where they can definitively say that there is a difference between a spontaneous cancer, a cancer that didn't arise as a result of radiation, and a cancer that did arise as a result of radiation. Therefore follows that looking at the DNA of Fukushima cancers is not going to tell you anything.
ありがとうございます。ブルーバイさんにもう一つ質問があります。よろしいでしょうか。福島県でですね、母子手帳を受け取ったお母さんにアンケート調査をしました。その時、その統計を調べてみても、先天性医療や死産は以前と変わらなかったという結果になっています。こういう進歩報道があります。
Congenital anomalies or stillbirth increases.
ブルーバイさんから示された妊婦さんの出産事例というのは、すべての妊婦さんについて調べられた統計の結果なんでしょうか。比較するとき、どういうことを気をつけなきゃいけないんでしょうか。
What kind of thing do we need to be cautious about when
Das, was mich beunruhigt an dieser Geschichte ist, dass die Schwanbelastung in Bayern nicht so hoch war.
まず最初に強調しておきたいというか、私を非常に不安にさせているのは、最初に見せたのはバイエルン州の例なんですけど、バイエルン州でのフォールアウトのその被
爆量というのは非常にもともと低かったんですね。で、それぐらいの被爆量というのは日本で多くの箇所であったわけですよね、福島の後。
But there was a lot of extreme amount of fallout in Fukushima.
Auch hier in der Umgebung von Fukushima in einem ziemlich großen Gebiet vorhanden sein wird.
ですから私はバイエルンで起こっていったようなことが福島とその周辺、そしてもうちょっと広い地域で実際に起こっているだろうと心配しています。
I am concerned that the same is happening in Fukushima and the surrounding environs.
ただ全体的に見ると先天性の奇形の発生率というのはそもそも非常に低いので。
It's very low to begin with.
Von Regierungsseite aus eine vollständige Erfassung der Fehlbildungen haben, um das hier gezielt untersuchen zu können.
ですからもっと正確なことを知るためには、例えば政府は日本全土で先天性奇形の発生率とかを把握するようにして、それを福島と比べるというようなことをわからないと思うんです。
I think that it would take that much to understand.
Da werden nicht alle Fehlbildungen erfasst, sondern nur die Fehlbildungen, die in bestimmten Krankenhäusern registriert wurden.
As far as I have heard, in Yokohama, regarding the birth of deformed babies, there is data being collected. However, that does not cover all births. This is only from certain hospitals where the data is being collected. So from that point of view, it's not possible to understand the overall situation.
Das ist deshalb so selten, weil die Probleme, die damit diskutiert werden können, alle unangenehm sind.
そもそもそういう機
thinking about the incidence of deformities, there are very few countries that actually collect data on the percentage, because the discussion that would occur as a result of that would be rather ugly. Therefore, no country is trying to collect that kind of data. And the reason that is, of course, there's the problem of radiation, but there are other factors that induce risk. For example, other chemical agents and other toxins that are in the environment. There's nothing clear in what I have presented, but if there's one thing that might be clear, then for congenital deformities to occur, that kind of genetic change is very sensitive. So there's a low-dose radiation that could have an impact to that. It could have to do with other chemical agents and other environmental toxins. It's a very sensitive issue. It's like a thermometer with which you would take your body temperature. I think that that's the role that it has. So if you're a pregnant mother, if you're expectant, and you survey them, and you discover that there are no issues, that still does not say that there really were no issues. So if there's a need to do something thorough, then you must apply political pressure so that either nationwide or at least near Fukushima, there is data collected to indicate what kind of dangers there are.
すみません、少しだけ補足を。報道では
Additional information according to the mass media, abnormality is at the same level as nationwide mean. However, for example, it's not 0.82%, so the 12. However, this is the result of overall Fukushima prefecture. If you look at area by area, abnormality is occurrence, including the heart of abnormality. That difference, for example, from 0 to 1.5, there's a wide variance. For example, the 20 there's quite increase in some kinds of abnormality. And every year, heart abnormalities as well as the congenital abnormalities together comes available. And I tried to accumulate 3 data for 3 years. However, this August must have get the latest information. However, still this year's data is not published. Therefore, if you look at the overall prefecture, the level is the same as the nationwide. However, if you look at the region by region, there are quite variations. And we are running out of time. Let's move on to the last question. Actually, there was a very important question.
労働者被爆の問題に関してですね、かなり国の大きな動きが出てきてるんですけれども、これ質問のバックグラウンドを知っていただくのがかなり難しいので、明日の演説でうまく載せたいというふうに思います。最後の質問はですね、ローゼンさんに対する質問で、趣旨が似た2つの質問を両方聞きたいと思います。一つは、今日アンスケアの報告書に対する詳細な批判をしてくださいましたけれども、実際に国連などでそういう批判を反映させて何か、世界に示していくというようなことができるんですか。そういうプロセスがもし可能であれば教えてくださいという質問。 それからもう一つは、日本側に突きつけられた質問で、ローゼンさんがご指摘になった JEA の、いわばデータの過小評価のようなものとか、スピーディーが、データとして使われていないみたいな話ですね。そういうものの責任です。責任に関して日本の司法に問いかけて、あるいはその国際司法裁判所のようなところに持ちかけて、その責任をはっきりさせるといいますか、問題にしていくということはできるんでしょうか。
Try to seek resolution to this issue.
Regarding the first question about the United Nations, I think what you have to understand is that the United Nations is a very political institution, and it is run by its member states. And the member states actually decide which topics are discussed and which topics are listened to. And in the case of anything having to do with ionizing radiation, with nuclear energy, nuclear power, there is a very strong lobby within the United Nations system of countries that have their own nuclear programs. And this is not just the United States. It is Germany, it is France, Great Britain, Russia, China, Japan, South Korea. So a large majority of the military, political, economic power in the world that has a huge interest in keeping this topic off the public radar. And for that, they have founded an organization or a subgroup within the United Nations called UNSCEAR, which has members that are appointed by these countries that have nuclear programs. So neither UNSCEAR nor the United Nations as a whole have a large interest in proving that nuclear power, that nuclear energy production causes significant health effects. And it's not just Fukushima. We're also talking about the health effects of the nuclear facilities. We're talking about health effects from uranium mining, like in Kazakhstan, or in Australia, or Canada, or in certain African countries. And it's a very big topic, and we have tried to bring this UNSCEAR critique to the United Nations. On the day that it was published by UNSCEAR, we organized a press conference in New York, opposite of the United Nations, together with Anna Grover, who is, or was at that time the UN human rights representative, or the person responsible for the universal right to health for the United Nations Human Rights Commission. And we tried to show the media, we tried to show the politicians that there is another side to the story, but it's very difficult to get through when there's so much political pressure to stick to the nuclear energies and the nuclear industry's point of the story. Regarding your second question, concerning Japanese issues, I did not say that JAEA underestimated the source term. What I said was they have an estimation that is much lower than the estimates of independent organizations. And I, for one, do not know which one is true or which one is closer to the truth. And I don't think that anyone really knows. But when I see independent researchers having significantly higher numbers than those who are employed by the nuclear industry, that makes me wonder, and it makes me think that perhaps someone is trying to hide something. So yes, I believe that JEA's numbers are too low, represent a systematic underestimate. But in the end, their estimate is also based on calculations and models. What I think, instead of going to the judicial system or going to the International Court of Justice, I think there's two things that you can do within Japan. One is to actually hold the scientific discussion that you are doing today in this conference, meaning that critical scientists, citizens, concerned parents, doctors, politicians, journalists, look at these numbers and say, wait a second, if independent researchers from Austria and Norway and other countries find that the danger is actually higher, then why are we only listening to the Japanese nuclear lobby? Why don't we take into account that there's other voices other independent research institutions. So this is a discussion that needs to happen, and it can influence the political discourse. And the second issue is, on a political level, there has to be accountability. And for me, it was very enlightening to read the damning critique of the Japanese Parliament's investigation commission, which very clearly stated that there is a level of corruption and collusion within the nuclear lobby, within the nuclear industry, that has actually contributed to the extent of this disaster, and which is not helpful in the aftermath in actually trying to discover what the health effects are. So, on a political level, as well as on a scientific and civil society level, there needs to be a dialogue about what happened in Fukushima and what the health effects are going to be. And we don't have 100% the truth, but the government and the nuclear industry don't either. And it's important to look for the closest approximation of the truth possible. And for that, we need independent research, independent politicians, independent journalism, with independent, and we most of all, independent from the nuclear industry.
ありがとうございました。非常に残った質問がいくつか
気になるものが多いので、なんとか整理して明日勉強に持ち込みたいと思います。どうも皆さん本当に長時間ありがとうございました。以上をもちまして、市民感染国際会議1日目が終了。
Day of the International Symposium on Radiation Protection. Thank you very much for your participation till the very last minute. Make sure to return the interpretation headset. When you leave, line up at the entrance to return the headset.
会場ですが、まもなく閉鎖になりますので、お話のある方は外のですね、会場の外のロビーでお話しください。よろしくお願いします。忘れ物ないようにお気をつけてお願いします。